Okay, let's start. Welcome everyone to the ITMP seminar. And today we are happy to have Gregory Gabadadze, and he will speak about new gravitational action for the trace anomaly. So please, you're welcome to start.
Thank you. I did not know who the audience will be, so I prepared few introductory slides. If they are redundant, just let me know and accelerate me. And I'm also happy to be interrupted at any point. That's all fine. So a brief reminder of quantum anomalies, although I'm pretty sure looking at the screen, you don't need this.
Gregory, I think you should not expect everybody knows everything. Yeah.
Okay. Okay, then I'll go as I planned.
Yes.
So the conversation is about field theories, local field theories, and as we know, very often there are symmetries in those theories, and we prefer the ones that have symmetries. Some of those symmetries are part of the nature, and some are beyond that. And we may hope that actually symmetry group is even larger than the one that we know. But those symmetries, some of those symmetries which are present at the classical level, are very often impossible to maintain at the quantum level. And that happens when you have at least two symmetries, two global symmetries. And very often at the quantum level, the consistency of your correlation functions is such that you are forced to give up one of those symmetries and not maintain it at the quantum level. The best known example is the axial anomaly that you are all familiar with. And I will come to that example on the next slide. But just to summarize, there is a clash between vector symmetry and the axial symmetry, which both are symmetries at the classical level as long as the theory is massless. And at the quantum level, one of them should be violated, and we choose to preserve vector symmetry because that has something to do with conservation of charges if we're talking about gauge electromagnetism or related. And axial symmetry is then broken at the quantum level. That's the axial anomaly. So what my talk is about is how to incorporate some of those quantum anomalies into classical effective actions. The action that I will be talking about is something that is not a fundamental action. It's an effective action in a sense that it has limited region of validity. However, that region of validity is pretty broad. Actually, it is sufficient for the description of the entire universe, astrophysics and cosmology, as you will see. So, to give you an example, a toy example, what I mean by capturing quantum anomalies in effective classical theories, let me discuss briefly a two-dimensional model, which many of you know well, and emphasize precisely that aspect as to how quantum anomaly, quantum axial anomaly in that model is captured in, or can be captured in classical equation motion. So this is 1 + 1 dimensional massless electrodynamics, also called the Schwinger model. You see the Lagrangian. The first term is the Maxwell term, and the next terms incorporate the fermion kinetic term as well as the interaction of the fermion with a gauge field. This is a Dirac fermion in 2 dimensions. The indices mu and nu run 0 and 1, and it is easy to figure out that the electric charge, well, this is the coupling constant. The coupling constant here have to be dimension full. Its dimensionality is the dimensionality of the mass in first power. Now, this theory has two internal global symmetries at the classical level. One is just what we call the U1 symmetry, just the phase rotation of the fermion field. Phase rotation of the fermion field. And the other one is the axial U1 symmetry. That's also the phase rotation, but with the I gamma phi in the phase, as you know. And that's a symmetry because there is no mass there for this fermion. And then we know that again in classical theory, according to Newton's theorem, there will be two conserved currents corresponding to this symmetry groups. While in quantum theory, what happens is that both of them cannot be maintained. If you look in detail at the correlation functions, respective two-point correlation functions, you will see that there is an explicit clash between maintaining the both. So we develop our normalization procedure so that the vector symmetry is maintained at the quantum level, but the axial symmetry is not. And this is the anomaly equation, which captures the breaking of the axial symmetry due to quantum anomaly. Epsilon alpha beta is the antisymmetric tensor in 2 dimensions, and F alpha beta is a field strength in 2 dimensions, the same one that was in the Maxwell term. Now, that's all well known, of course, and the content of this slide is also well known. This model can be bosonized, meaning that all the fermionic fields can be rewritten in terms of a certain boson field. And then there is a nice paper going back to 1970s, how to do that. Let me just capture or summarize briefly the aspects of that bosonization which are important for the point that I would like to make. Through the bosonization, you can express the vector current as follows. It's the epsilon tensor multiplied by the derivative of the scalar field phi with some normalization in front. And then, as you know, in 2 dimensions, there is a explicit relation between gamma phi times gamma alpha and epsilon alpha beta times gamma beta. And because of that, there is an explicit connection between the axial current and the vector current, very special one, specific to 2 dimensions. And due to that property, for the axial current, you get this expression. Now, as you can see from the construction, this vector current is automatically conserved. Once you take the derivative of this, this is automatically 0 because antisymmetry of the epsilon tensor, while the vector current will give you the conservation of the vector current or derivative of the vector, I'm sorry, the derivative of the axial current will give you D'Alembertian acting on phi. And if you use the Maxwell equations, so this is the Maxwell equation, d mu f mu nu equals to j nu, and instead of j nu, I substituted here this expression, bosonized expression. And the second equation is just the anomaly equation, but rewritten in terms of phi. So box phi equals to this. So these are 2 equations which have only bosonic fields in them. You have a vector field and the scalar phi. That's point number 1. Point number 2 is that they capture quantum physics, part of quantum physics at least, which is this anomaly equation. Now you can ask the following question. Is there a Lagrangian, a local Lagrangian that one can write down so that these 2 equations are classical equations that you get when you vary that Lagrangian with respect to the vector field and the scalar field? And it's very easy to answer that question. The lowest order Lagrangian is this. Again, the Maxwell term for obvious reasons, because you need to maintain this term. There has to be a mixing term between phi and the vector field because you need to get this term in the Maxwell equation and vice versa. You also need to get this term in the anomaly equation. So this mixing term guarantees that. And then you have to have the kinetic term for the phi field because you have box phi over there. So that's the Lagrangian, which if looked as a classical theory will give you the equations of motion that capture quantum anomaly. Then that Lagrangian also captures respective physics. As you know, the Schwinger model at the quantum level has a mass gap. The reason why it has a mass gap is precisely the dimensionful nature of the coupling constant E. The way you typically see, or well, one way to see that in the Schwinger model in terms of the basic variables of fermions and the gauge bosons is that you look at the one-loop diagram, one-loop polarization diagram, for the vector field. And if you resum those bubbles, you will find out that there is a pole in the resum propagator, and that pole is precisely m squared at m squared equals to e squared divided by pi. So whatever degree of freedom you have is a massive degree of freedom. Now you may ask, what's that degree of freedom? Vector field to begin with had 0 degrees of freedom because you have 2 components in the vector field and both of them can be eliminated by gauge. They are both gauge redundancies. So there is, to start with, classically there's 0 degrees of freedom there, but then fermion anti-fermion pair, so to speak, at a quantum level provides some effective degree of freedom, which is in a way eaten by that vector field. And as a result, you get 1 degree of freedom, 1 longitudinal degree of freedom, which is massive. In some ways, this is similar to a plasma, perhaps, except that this is all Lorentz invariant, of course. So, this Lagrangian, then, this classical Lagrangian captures all that physics very well. You can diagonalize, you can go to a simple gauge and then diagonalize this. When you do that, you're going to get just massive scalar field, phi, and the remaining terms here will be actually Gauss's law, what you would consider to be a Gauss's law. And since you always impose that Gauss's law on the states in let's say in A0 equals to 0 gauge, then your Lagrangian is just free Lagrangian of a massive scalar. So physics is also captured by this. So this is kind of a dream scenario what one would want to accomplish in gravity. Obviously, gravitational theory will be very different. There will be nothing exact about it. While here everything is exact, thanks to the integrability of this model, in fact. But in essence, this is what one would like to achieve, to write down some effective field theory valid below a certain scale, which is calculable. The effective field theory equations are calculable, and use those equations which capture anomaly for the description of physics. So let me get to that now. Let me begin reminding you about phase anomaly. It's also called scale anomaly, sometimes while anomaly. If you have no gravitational field present in a simple theory of a, let's say, a vector field, let's say massless vector field, interacting with, let's say, fermions, massless fermions, for simplicity, the stress trace of the stress tensor T mu will be proportional to the beta function of the theory multiplied by the field strengths. And now I'm in 4 dimensions, and unlike in 2 dimensions, my time signature is minus. Now in the spatial signature is plus. This was already noticed long ago in terms of the correlation functions, but this operator relation in quantum field theory was derived a little bit later than that, but that's not important for now. So what we like is to include gravity, and in fact, most of the attention will be paid to the gravitational field. The gauge field part of this construction is, in a sense, simple. So I won't be emphasizing this. I won't even mention too much the gauge fields, because the gravitational part of the gravitational field is non-trivial and problematic, and that's a problem that I'm addressing here. So gravity will be regarded as a classical field, classical dynamical field. That's a good approximation at scales way below the Planck scale. And I will always stay way below the Planck scale. And that will be important. And you can imagine now coupling gravity to some conformal sector, or coupling to the standard model, which has massive fields too. But in general, we know how to deal with the massive fields, so I'm not writing them here. But for the massless fields, the stress tensor will develop the scale anomaly in this external dynamical gravitational field, and it's being long known the form of that anomaly. It's some coefficient A, which depends on the content, particle content of that CFT, and also the representations of in which those particles are, times the Euler invariant or Gauss-Bonnet invariant, which is expressible in terms of squares of the curvature, is given here. And then there is another term which has coefficient called C in front, which is multiplying the wild tensor squared. W is a wild tensor, and if you square it, you're gonna get this combination. In literature, typically this C is minus C, but for simplicity, I just use plus. Now there is also term B times box R, and this term is somewhat arbitrary because in the respective effective action, any addition of any Ricci scalar squared on the equations of motion will give you this kind of term, and that R square coefficient is arbitrary, and because of that, you can just drop it for simplicity, or you can add it with arbitrary coefficient if you'd like. In the effective action, it will be just an additional R square term, but I don't want to carry it around in my equations. So I'll be focusing on these two terms, and even between those two terms, the first term will be the key for me because that's a term that gives rise to typical problem that I would like to talk about and the resolution of the problem. So C times W square will be again easy to incorporate in what I talk. This is the Einstein's trace of the Einstein's equation, in which in the right hand side now I substituted the trace of the energy momentum tensor, and you see that these are higher dimensional terms. They have squares of Ricci scalar, and you would immediately ask the question, well, how about an infinite number of them, which you would expect from some high energy physics? And as I will argue, there is a framework in which you can just retain this and neglect all the others and treat this theory as an effective theory up until some scale. So the question then is, what is the ineffective Lagrangian variation of which can give rise to that equation and retain all the nice features of GR? Well, this question was asked and answered actually in papers which were almost simultaneous or simultaneous for all practical purposes. That's Rigert and Efim Fratkin and Arkady Zeitlin in '84. They are in the same journal. I think might be back to back or maybe very small difference. In any case, it's a simultaneous. So let me. Rigert's construction is a little bit more general. It's done in the context of GR. Fratkin and Zeitlin construction is in context of conformal gravity, but that's not creating any difference for this anomaly piece that I'm going to talk about. It's all the same. The generality, little bit generality of the Rigert is in a sense of his constrained equation on the fields was less restrictive than in Fratkin Zeitlin. But again, that won't matter at all, to tell the truth. And in the literature, this goes under the Rigert's name. It's called the Rigert action. But as I mentioned, these papers are simultaneous. Actually, the results are the same. So you need to find out some action denoted here as SA tilde, which is a functional of G and of course derivatives of G, but I'm not going to write that for simplicity. Such that when you take variation of that action with respect to the metric tensor and trace it, you want to get the trace anomaly. If you achieve that, then you can just combine this SA tilde with the GR action, and you will get the correct, at least correct the trace equation, including the quantum anomaly. And then you can try to solve it for various astrophysical settings, cosmological settings. Those solutions might be interesting because they will be capturing some quantum physics, effective quantum physics of the CFT or the general QFT that you've loops of which you've taken into account. However, one can argue, and this is well explicit and implicit also in Rigert's paper, that this SA of G cannot be a local action as long as one insists it to be a function of only G and derivative of G, of course. For that reason, what actually both papers do is separate G in terms of this conformal factor and G bar. Now, in general relativity, this is entirely arbitrary separation, as you know, because there is a local symmetry shifting sigma by any function and rotating G bar with the exponent of the same function with opposite sign, like Wild transformation of G bar and sigma, which keeps G fixed but changes sigma and G bar. Therefore, this sigma, if you just insert this into GR, this sigma is just gauge removable. It's just, with Wild symmetry. But what Rieger did, as well as Tatkin and Zeitlin in somewhat different ways, is they constructed a functional, which is called SA, now without tilde, to make a point that it depends separately on G bar and sigma. It doesn't depend on this combination. Therefore, that Wild symmetry is not a symmetry of this functional, SA. And that functional has this form written down below. And again, what's important is the A term. So I'm going to be focusing on the A term. You got d4x, obviously square root of minus G bar. Then the sigma field multiplies E bar. E bar is the Gauss-Bonnet invariant, but written for the Bard metric. And then you got G alpha beta. This has to have a bar. It's a typo here. G alpha beta is the Einstein's tensor for the Bard metric, contracted with covariant derivatives of the sigmas with respect to the Bard metric. And then you have two more terms, which are called Galileon terms, actually, in modern language, which emerged also in very different constructions. Nevertheless, they emerge here too. So one is just, what's called cubic Galileon. It's just D'Alembertian of sigma multiplied by derivative of sigma squared. And then there's a quartic Galileon, which is the derivative of sigma to the fourth, with fixed coefficients between the two, so that actually they realize nonlinearly scale invariance. So that's what they've derived. The important property, and as I said, the other term is trivial because it's scale invariant. I'm not going to be talking too much about the W bar squared. So you can write this as W bar squared G bar or as G W squared because it's just scale invariant. So I'm not going to be talking about. So now, what was well, first a good thing. Good thing is that if you combine this with the GR action, in which you can substitute now e to the 2 sigma times G bar, and if you take variation with respect to sigma, you're going to get the right trace anomaly equation. Now, what was the problem in Rieger's paper, or rather he thought it was a problem and went beyond this action into some non-local actions. Actually, in his construction, in Rieger's construction, he imposed a condition on G bar for it to have fixed determinant. So G bar he had fixed determinant in his construction. As a result, he Rieger regarded this action as being non-covariant. And because of that, in the second part of his papers, he tries to express this sigma in terms of G by using certain fourth order operator, and in that fourth order operator then introduces issues in that expansion because it gives you 4 derivative theory and with ghosts. But there is no need to do that. There is no need to do that. This action by itself is already a good, legitimate, effective field theory. First pointed out by Komargodski and Schwimmer in a different context. They proved the A theorem. I'm not going to talk about that, but most of you know that. And they've reconstructed this action without imposing any constraints on this G bar, just as an action which gives you, Wild anomaly, period. And moreover, if you go back to, let's say, Rieger's paper, it's easy to say, to think why this is true, that this is it, this is the answer. because sure, you can impose some condition on the determinant of G bar and derive this action through that, but that's a technical detail. In the end, once you derive, you can say, let me take this action and declare G bar to be a tensor, full-scale tensor with all the diff transformations, and gauge fixed version of that you can regard to be the Rigert construction if you like. But the full theory, this theory is diff-invariant. Actually, as long as you treat this in a fully diff-invariant way, you're gonna get diff-invariant. This is a diff-invariant theory. So Komarowski and Schumer, of course, derived that. Another interesting thing, right after, just a few years ago, my former student and I derived this action as a Vesumino term in a coset of SO 2,4 over ISO 1,3. So this is a theory. You postulate that you're starting with a theory which is fully conformal invariant in 4 dimensions. And then you assume that conformal invariance is spontaneously broken down to the Poincaré symmetry, and you follow the standard coset construction, and you will find out that this term exactly comes out as the Vesumino term. In fact, there is a 5-dimensional way of writing this term, and a pullback of that 5-dimensional term on a 4-dimensional boundary gives you exactly this term. So these 2 papers then put the whole thing on a more solid ground in terms of this being just an effective field theory that you can address further. One comment in regards to relations to the 2-dimensional theories. This is exact analogy of the Polyakov's 2-dimensional action in which you resolve R1 over box R by introducing a scalar field, which you can call pi. So you're gonna get the action which will be pi times R minus d pi squared. So this is exact 4-dimensional analog of that theory. As I said, it gives you the right action. Okay, so then what's the problem? Why this theory, general relativity plus Rigert-Radkin-Zeitlin action, why that's not the answer to the question that we're asking. It gives you trace anomaly equation here. It has most likely it retains GR properties up until some scale at which these new terms kick in. So why that is not an answer? The reason why that is not an answer is because this sigma field, the scalar field, is infinitely strongly coupled in that theory. And here is what I mean. You can, for instance, there's many ways to see this. One way is that you can go back to the Einstein frame, write GR action is now G, and rewrite the anomalous action in terms of G and sigma. It will have the same structure. It's just some coefficients change in those 4 terms that I wrote, but it has the same structure. And then you are, as you know, this redefinition in GR just entirely removes sigma field. There is no sigma field in GR. But then you got the higher derivative terms, well, higher dimensional terms, I should say, such as this, there. And moment you are in that business, you know that this theory is infinitely strongly coupled. So those terms are written here schematically. The Einstein tensor times the 2 derivatives sigma, then cubic Galileon, quartic Galileon, and no kinetic term for this sigma. So if you are in Minkowski space, the way you can think about it is that you can introduce the kinetic term with some coefficient z, in which z goes to 0, and include any of this. Let's say the simplest one would be this to the 4th power. If you rescale the sigma field to canonical, so you have now canonical kinetic term for sigma, but its quartic interaction is suppressed by z to the 4, or divided by z to the 4, I should say. And since z goes to 0, that's blowing up. In terms of amplitudes, if you want to scatter, 2 sigmas into 2 sigmas, simplest amplitude through this vertex, you're going to get S square Mandelstam variable squared divided by z to the 4th, and that amplitude blows up. So it's an infinitely strongly coupled theory at arbitrarily low energy scale. There is a problem.
Excuse me, Giga, may I ask a question at this point?
Yes.
So if you look at the equation at the top of the slide,
Yes.
it would seem that actually the equality here is not entirely legitimate, because if you just reparameterize from G bar to G,
Yep.
then actually the second term, your action SA, Rigert action,
Yeah.
will have the form, the second argument of in the second line, in the last term, will be not just G, but G to the power times E to the power minus 2 sigma.
Yeah.
Then I'm afraid that this term will also get the kinetic term for sigma.
No. Yeah, you are right, Andre, but I've already included that. Maybe I should call this SA prime. This is a comment that I was making. Let me call this SA prime of sigma and G to make a point that it does not coincide with this one. You see my cursor, right? It doesn't coincide this one, but it's a transformation of this one that you are talking about. And it's totally expressible in terms of sigma and G. So in this new action, when I do the change of variable, I'm gonna get, square root of minus G here. Then I will have sigma times E of G, no bar. I believe this term, the shape is the same, but the coefficient will change the sign when you combine all the terms. And one of these terms also changes the sign. It's not the same action. It's clearly a different action in terms of, how these terms are arranged, but the structure is similar. In particular, what's important.
So you want to say that it will still not have a quadratic term in sigma?
Exactly, you are exactly right. It won't have the quadratic term in sigma. Yes. And it will have these higher dimensional terms. It will have cubic Galileon, it will have quartic Galileon with different, one of them will come with different sign. Can't remember which one, but I think it's this one will come with different sign. And it will also have this term with different sign. So
but still, it is a little bit strange, because if you look at the first line, well, just get back to the slide. Yeah, if you consider the first line and take it at face value, then it would seem that you have the kinetic term for sigma coming from the first term, from the first line, from the first term.
That's exactly
right. It will be a ghost.
Yes, that's exactly right. Yeah. So let me comment on that. So that what you just said, Andre, is also correct. That's the GR, has nothing to do with SA. Let me put aside SA for a second. In the GR, as you say, if I rewrite GR in terms of G bar and sigma, I'm gonna get the Einstein-Hilbert term for G bar multiplied by e to the 2 sigma, and then I'm gonna get kinetic term for sigma with a wrong sign, the ghost sign. Now you would say, well, GR has a ghost. Well, it doesn't, because when you wrote this way, there is a wild symmetry in GR, of course, by which you would just gauge away that sigma, right? And we know that degrees of freedom of GR are just Punkt-tensor modes. So that's just a trivial statement which I'm making, because that's a fact that I can rewrite it in this form. So that kinetic term is completely absorbable in the Einstein-Hilbert action written in terms of G. That's the whole point. If it weren't, then we would have different conversation, but it is. But this transforms as I described. It changes from the previous form, but retains these higher dimensional terms and doesn't generate the kinetic term for sigma. Yes.
Okay.
Yep. All right.
I also have a question about previous transparent.
Yes.
Okay, but in the second line of your action SA, you have no sigma, right?
Yes, sigma is just a conformal. You can yes, you can. This one is while invariant.
Yeah. Okay, and usually what such invariant squared has ghost when you.
Yes, you are exactly right. I will come to that point. So this operator will be in the end will be suppressed by higher scale than the operators that I would like to keep. So these operators will be kept. The Rigert-Radkin-Zeitlin piece will be kept. This will be higher, somewhat higher scale operator. So that means that you should never go to that scale. Otherwise, of course, you get more than 2 derivatives in the equations of motion. And that's just part of that effective field theory completion, whatever completes this theory at that scale. But the point is that these pieces will be suppressed by lower scale. So they'll be relevant at lower scale. And they are different from the wild piece because they never give you more than 2 derivatives per field in the equations of motion, or they don't have these Ostrogradsky ghosts. That's a known property of these Galileon theories, and then it goes under more general name. These are called Horndeski type theories. So Horndeski has written, as you know, this general class of theories of a scalar interacting with tensor field so that equations of motion are always second order. So that is the equivalent to the statement that you never get these Ostrogradsky ghosts in this part. And that's the part that I'm going to be focusing, because that will be at a low energy scale. And you're exactly right that this would, if I were to keep physics related to this, that would be a complication. It wouldn't be legitimate, in fact.
Thank you.
Sorry, could you please explain one thing concerning this strongly coupled theory? So is there anything particularly bad about it if you just, I don't know, if you don't try to rephrase it as reintroduce this two-derivative term? I mean, is there anything fundamentally wrong with it? I don't know, like non-stability or something?
Yeah, it's very unstable in terms of, if you like to formulate that the same problem in terms of the stability. Yes, it's very easy because now let me not introduce this. I think this is what you asked not to introduce, correct? Z squared times this.
Yeah.
Let me not introduce this, but let me take extremely weak gravitational background. For instance, a background of a planet far away from planet, very weak, right? So clearly this G will have, okay, maybe not literally G, but or not literally planet. It's some kind of dust, some kind of distribution, right? Very weak, low density dust. So then this G won't be 0.
Okay, so
it will be very low and it won't be 0. So that will give the kinetic term for this sigma. A, the sign of that kinetic term depends on the background that you choose. B, you got now effectively this sort of term with very small coefficients in front, which tells you that, yes, there is the sigma field propagating on it, but it's very strongly coupled, very strongly coupled. That means that that's not a realistic description of our nature, actually. Those in that kind of world, the sigma fields will be scattering very strongly at very weak backgrounds already. So clearly in our world, that is not happening.
But here I would also say that what you're trying to do, you're trying to solve this equation by expanding it into plane waves, right? And you are just saying that this expansion is singular.
No, not well. It's not singular. It's you can definitely expand. Let's say you have weak background, you can definitely expand. There is no problem with that. It's just about the strengths of nonlinear interactions of those modes. That's the issue.
Yeah, well, I just mean that normally the kinetic term is dominant, and that's why it's reasonable to do this kind of expansion. But here it's not dominant, so maybe just one should not use this expansion and you use a perturbative scheme, and then the theory is totally fine.
Well, yes, if you manage to find some exact, essentially, then you would be asking some sort of exact solutions of this. And making sense of this theory in the context of that exact solution. Well, maybe, I don't know. But for applications to real world, that is a strong enough argument already, the one that I'm making, to declare the problem. The reason why is because we do have curvatures in our universe, which are very reasonable curvatures. They are low curvatures as compared to Planck scale or anything. And any of those curvatures will create this term for sure. That will be quadratic perturbation. Then for sure, I do have scales below those curvature scales at which I can quantize this or look at the plane wave solutions on the respective background. And all the arguments that I just made are legitimate in that scale. And that will tell you that those fluctuations will become strong. So what you are saying is that, yes, they become strong, but then perhaps I know how to resum them exactly. Well, that's sure, possibly, but that's a very difficult proposition.
Oh, okay, thank you.
Sorry, may I ask also a question?
Sure.
About this z-squared term.
Yes.
So you try to remove it by rescaling sigma, but
Yes.
instead you could rescale axis, I mean coordinates. Suppose it is in flat space-time.
Yes.
Because it should be integrated with usual measure. Then it will disappear in both terms.
Okay, maybe between the two terms they might, but they have different scalings, I believe. So that will be very hard proposal because you also couple this to the normal, particles or normal matter, and they all have different scalings with respect to the derivatives. And then the backgrounds will also have to rescale. So I doubt that you will be able to get rid of everything. And the reason why is because based on dimensional arguments, right? So this should be leading and this should be subleading. And then you ask, what's the scale at which the change happens between the two? That scale, you cannot just figure out from this Lagrangian unless either you introduce small backgrounds or introduce the small z exercise, as I was just saying. And then you see that transition physically between the place where kinetic term dominates and the next term dominates is determined by the scale of the background, physical scale of the background. So because of that, I don't think you can remove this difficulty by the rescaling that you just mentioned.
Okay, and just a comment that for cosmological background, G could be cosmological constant.
Yeah, sure. That's one example, sure. And you see that, well, thanks for that. You see that there is another issue here. If I take de Sitter or anti-de Sitter, for one of them, I'm gonna get good sign kinetic term. And for the other one, I'm gonna get wrong sign kinetic term for the sigma. So clearly that theory is already making for me unhappy because I want both de Sitter and anti-de Sitter solutions to be stable, at least at some low energies. And this one wouldn't allow you to have that.
Do you remember in which case you have good kinetic?
I don't, to tell you the truth.
But it's easy to see.
Yeah, it depends, of course, on the sign of this coefficient in front. There is this A, that depends on the field content and also normalization that I used. Because of that, I don't remember which one.
It would be interesting if de Sitter, for instance, would be fine and anti-de Sitter is bad.
Maybe if you take that question in isolation, but for me, this theory is problematic because I can take many other backgrounds, very realistic ones actually. You can do many exercises and see all sorts of weirdness if you only retain this term and no additional kinetic terms, such as superluminal propagation. Very easy to get superluminal propagation on very reasonable background simply because you kind of enhance here the spatial components and not the time component, and so on and so forth. All sorts of the gradient instabilities by flipping those signs. So this theory is really, really problematic in many ways.
Okay, thank you very much.
So, and that's the problem that we would like to solve, at least within some reasonable effective field theory framework. And now to guess a solution or to get an intuition as to how to solve, let me kind of dig a little bit deeper to identify the origin of the problem. Where is this coming from? I mean, is it some sort of accident that we wrote this effective action and somehow it has this issue, or there is a fundamental problem? There is actually this problem can be formulated in very clear statement. It has something to do with the fact that in general relativity, the conformal mode is not a physical mode. It's not a propagating mode. And what we mean by that is shown here in one particular example. Let's expand around flat space. You don't have to, but this is simplest. If you expand around flat space and decompose in a standard way, H00 is 2 times n, and H0j is, let's say this is a transverse vector and this is a longitudinal part, and then Hij you decompose in a standard way, again, it's transverse traceless tensor, this is a transverse vector, and this is the gauge-dependent piece, and this is a conformal mode. Okay, and write down the Einstein-Hilbert action in the quadratic approximation in terms of these fields. So you know what you get for transverse traceless tensors. That's just your gravitational waves. That's well known. You also get separate, but you also get separate Lagrangian for the scalar pieces, scalar parts of this decomposition, which is what I wanted to emphasize. And this is what you get for tau. So there is a first term with a negative tau sign. So it's a ghost-like term. Well, there is nothing new about that, right? So you knew that in GR, if you just substitute e to the sigma times flat space metric, that sigma is going to be the ghost. So this is what it is. You, of course, get the kinetic term for the tau2. I'm sorry, the gradient term for the tau2 is here. But you also get the lapse multiplying the Laplacian of the tau. And the lapse in GR, as you know, enters as Lagrange multiplier linearly as well as non-linearly. So if you vary with respect to lapse, you're going to get the Laplacian tau is 0. So tau can have, I'm imposing, boundary conditions, so everything decays. So that means that tau can only have time dependence. That's fine. That's your cosmology, actually. This tau formulated this way is the scale factor in FRW cosmology. And you know that the scale factor in FRW cosmology, when you go to mini superspace, it has a ghost sign in front. Of course, we don't worry about that simply because you know that there is no propagating mode corresponding to that. And the reason why there is no propagating mode is because it's constrained, like so. So that's the point, that in GR, there is no propagation for a conformal mode. This also goes back to what Andrei was asking before of absorbing that sigma into GR action. It's all consistent. It's all pieces of one story. So that's the fact. And then all of a sudden in the anomaly action, you do get that conformal mode back as a mode which is not removable, but with higher derivative pieces. And that's where the problem comes from. Precisely, as I described. No kinetic term, but some high nonlinear terms. So that's what you want to solve. So how to solve it? One way is this. This is what I proposed. So instead of GR, you start with GR. This is GR. M is just M Planck divided by square root of 2, but I'm going to keep M for simplicity. And I'm going to accelerate a little bit because I might run out of time. So this is the GR piece. And from the GR, you subtract another piece, which is GR, but written in terms of G bar, with another coefficient in front, M bar. M bar will always be smaller than M. That's the input parameter in this theory. It's a lot smaller than M Planck, and all the physics that I'll be discussing will be at the scale M bar, way below M Planck. So that's why I can ignore all the M Planck related physics. So that's what's written here. Epsilon is a ratio of M bar and M, and it's much less than 1. Now, how the introduction of this piece modifies what I just told you on previous slide, you can do exactly the same thing. You look at the fluctuations, and then in addition to this piece, which was on the previous slide, you get another piece, which is weighted by epsilon, but in that piece, you have now combination of tau and sigma introduced through this. And again, you get a constraint because you're not violating, constraint structure of general relativity. This is still general relativity plus a scalar, actually. But constraint is now gets modified. It's a Laplacian of this combination that has to be 0. And if you resolve this constraint and substitute back, you're gonna get now a legitimate Lagrangian for tau. So it's here. So this d tau stands for d mu tau squared, and the coefficient in front is this. As I said, epsilon is much less than 1. This minus is the right sign here, because I'm using mostly plus signature. This is not a ghost. This is the normal scalar field. Or you can rewrite everything in terms of sigma. So sigma and tau are interchangeable. They mix, and one of them is dynamical. The other one is not. Other one is still constrained as it was in GR, right?
Excuse me, Giga.
Yes.
What prevents you actually to consider the case when m bar is nearly equal to the m? You will get in the last in this kinetic term in the last line for the Lagrangian. You see, you get nearly 0 at the denominator. So again, this is a very good situation when sigma becomes very, very, very weakly coupled.
Right, you're right, but there are other considerations, which is that if m bar is of order m Planck, in general, I have infinite number of other operators, and I cannot retain what I'm retaining and ignore the others. I need that hierarchy to tell you that here is an effective Lagrangian written in terms of few terms and not an infinite number of terms, which is a good approximation at that scale. At that scale will be m bar. So you will see this. That's one point. Another point is that when you're thinking in terms of the nonlinear self-interactions of sigma, that's true that they will be very much suppressed, Andre, as you just said, because of the reasons that you said. But there is also, because there is a mixing between sigma and the graviton, there will be linear, there could be, depending on the framework, could be linear interaction between sigma and the stress tensor, which is m bar over m. So if you take m bar close to m, that will be also sizable, comparable with gravity, which will rule out the theory.
But this depends very much on how you couple your sigma to matter.
Exactly, I agree with you. So there is a way.
Special discussion, I believe.
Yes, I agree with you very much. There is a way to avoid that by using certain symmetry-based coupling, which are used, in fact. But the previous problem that I mentioned will remain. So that is why I'm taking that hierarchy, m bar a lot smaller than m. Okay, so this is another way of rewriting this theory, which is more familiar to everybody. The Einstein-Hilbert term, and then here is a conformally coupled scalar phi to GR, where this conformally coupled scalar has a VAV, which is m bar, and its fluctuation is sigma. It's just a rewriting of the previous thing. And interestingly, this theory has a symmetry which mixes these two parts, the GR part and the new part, R bar, I call it the R bar part. This symmetry mixes the two. Here it looks complicated and mysterious, but there is a nonlinear transformation which you can do to reduce this theory to tensor and a scalar. And in that language, this symmetry is nothing but shift symmetry of some scalar which has very complicated form in terms of this scalar. Anyway, and then there is coupling to matter, as Andre was just pointing out. Because this is not a fundamental theory, it's not a priori clear which of these tensors should couple to matter. There are essentially two choices. One is that G couples to matter, and another choice is G hat couples to matter. G hat is related to G through this relation. And the interesting fact is that if you couple to G hat the matter, then this symmetry is also a symmetry of the matter sector. So that means that when you start looking at the matter loops, they won't be generating some mass terms for phi and the quartic term for phi. And that's the reason why I consider this coupling. Otherwise, if you couple to G, phenomenologically, it's very similar to coupling to G hat, modulo those corrections that Andre just talked about and I talked about. But fundamentally, through quantum loops, you will be generating more terms in that scenario. So I'm happy to talk about it, but let me let me skip some of this. This is just the conversation about the higher dimensional operators. The point is that in this theory, and I will summarize those here. So the proposal is this, that the full classical effective theory, which captures the trace anomaly, has this form. This is the Einstein-Hilbert action written in the Jordan frame in terms of sigma and G bar, but you can rewrite in terms of the Einstein frame, no problem. This is the R bar term with the minus sign. And because it has minus sign, that's precisely why it gives you the right sign for the conformal mode, for the sigma mode, I should say. And this is the anomalous action, the Rigert-Bradkin-Zeitlin anomalous action here. Now, let me summarize what I wanted to say on the previous slide. If you now rescale fields properly with appropriate scales, you will find out that this last term will be suppressed by at least 2 powers of m Planck and 1 power of m bar. And that's a higher scale than just m bar scale. So the only terms which will be suppressed by m bar scale are here. And because m bar is a lot lower than m Planck, then I can retain these ones and neglect all the other ones. And there could be many other ones coming from, Planckian physics, whether it's, particle physics or perhaps gravity even. But those are, you can be agnostic to those terms because this is a lot lower scale. And then that lot lower scale, this will give you the dominant contributions. So the equation is straightforward to get. You just take a variation and you get this equation up to, again, Planckian corrections. Corrections suppressed by m Planck, and those corrections are not fixed here anyway, so you can just ignore them. It's the right equation. And then, of course, you get all the other equations, right? So you get GR with an additional scalar, which has very specific nonlinear interactions, self-interactions, as well as interactions with gravity. Now, after I put this on the archive, Pedro Fernandez sent me his paper written a couple of years ago, which he came to almost identical action like this from very different principles, having nothing to do with anomalies. He was asking the following question. Let's say, have a theory which breaks scale invariance, but has equations of motion which are scale invariant. Theory of a scalar in the tensor. And from that condition, he just restored this action. He had this action. So it's very interesting that such very different principles gave to the same action. And obviously, I revised and quoted his paper, and it's all both are, in that sense, they're consistent. And let me reinforce the point that I was making about m bar scale suppressing the nonlinear interactions, because that might have been a little quick. So you can take a limit. M goes to infinity. This a physical limit here is that Planck scale is a higher scale. Everything else is way below Planck scale, and m bar is fixed. So in that case, this pi, which is rescaling of sigma with m bar, kind of decouples from gravity because you've taken and Planck constant goes to infinity limit. Then it has its own dynamics, and you can take that theory from previous slide and take the limit, and you're gonna get the kinetic term, good kinetic term for the pi field, coming from this R bar term precisely that we included. And then you got obviously, cubic Galileon and quartic Galileon, both of them suppressed by m bar. So they are dominant nonlinear interactions. And again, going back to conversations about, how many derivatives, these are theories in which you retain 2 derivatives. There is no ghost related to these pi interactions, additional Otrogradsky ghost. This goes back to Sergei Vernov's question because of special structure of this. So recently, just last week, I think it was maybe 10 days ago, Tsujikawa found a black hole solution in this, in some approximation. In the leading approximation, in this parameter A, suppressed by m bar scale. So those are the most important corrections. Those are the corrections which are due to these pieces, not some m Planck suppressed physics that we are ignoring. and he found them explicitly. And then there is a fifth force. Because of that, there is a fifth force, which is proportional to his alpha is my A, so I should have used A here. A times m bar over m Planck squared. You see, Andre, this is additional piece, which is not coming from R minus R bar, in which you could have removed that fifth force by using coupling to matter through G hat. But this is coming from the anomalous piece. It's proportional to A, and then there is m bar over m Planck squared. So clearly this fifth force should be suppressed as well. So you cannot go too close to Planck scale. But this may have some interesting, well, these effects will impose constraints on this m bar. This m bar is a parameter in this field. So just to conclude, so the arguments that I made was that SA by itself combined with GR is a infinitely strongly coupled theory, and that argument, by the way, was already made in the literature in a different context, in the context of some Gauss-Bonnet constructions in 5D. And it is clear as to why, because the conformal mode in GR is not a propagating degree of freedom. But you can solve this problem, and one way to do that is to amend the GR by this R bar term. It's the same Einstein-Hilbert term with opposite sign, but depends on m bar and G bar. And in plain language, in physics language, that means that this proposal introduces an additional scalar degree of freedom and an additional physical scale, m bar, which is below m Planck. And those are the things that can be tested, and bounds can be imposed on in this m bar. But that's what seems to be required for taming this infinitely strongly coupled behavior in trace anomaly, or else you would need to modify the particle content so that the trace anomaly cancels. And I think Arkady and Bradkin did have various models in which that was the case. So either you need to do this, or you need to cancel trace anomaly. In either case, you are introducing additional low energy degrees of freedom. So I will stop here.
Okay, thank you for a nice talk. Are there any questions?
Well, it would seem that you could have reached the same goals by playing around with the coefficient of the box term. You see, this will be equivalent to introducing not the Einstein term of G bar, but you could have added something like R squared of G term.
Oh,
like
yeah.
Starobinsky model.
Yeah, well, R square of G, that I don't want to add R square terms, as I was mentioning, right? Because because they introduce additional massive degrees of freedom, which are typically problematic. So this goes into the ghost Ostrogradsky ghost type.
No. Starobinsky action is okay in the sense of Ostrogradsky ghost.
Yes.
It's just the question of proper choice of this coupling constant. There is some positivity range where the kinetic term will be okay.
Well, yeah,
I think that you could have done the same, but with this.
So there is a little bit might be a little terminology. So if you only add R square, literally the Ricci scalar.
Yeah.
Ricci scalar.
Where?
Sure, there you can choose the signs in a way that the Ostrogradsky ghosts are not there, but this is a new kind of scalar massive scalar that you are introducing. In general, general Starobinsky model, there is other terms as well, and those typically introduce the ghost. That's what I was referring to. That's how you get. I believe that's how you get the instability on the Starobinsky inflation. But never mind that. If you introduce the R square term, it's the same. So just R square term itself won't give you what you need. You can introduce R square in terms of G bar. Then if you do that, sure, you will get some quadratic terms for sigma, but those quadratic terms for sigma will be again weighted by some curvatures. And it will be curvature dependent.
No, I think no, it will be not weighted by curvature. I think it will have a good expansion on flat space background.
Well, it's easy to do, right? So R, you can rewrite. Well, I'm talking about R bar now. R bar.
Yeah, R bar squared.
Yeah, R bar squared. So in R bar squared, I can rewrite as, R plus. There is conformal factor times R plus kinetic term for sigma. True. Now I have to square that. When I square, sure, I get again R squared with some conformal factors. I get mixing term between R and kinetic term of the conformal factor, and then I get derivative of conformal factor to the fourth power. Yes. So the two derivative term for the conformal factor is multiplied by the curvature written in the Einstein frame.
Well, I think we have to consider it more carefully. Well, it's impossible, I believe, to.
Yeah, we can consider more carefully. I've done this at some.
You have to get
yes.
more in details of this derivation.
Yeah. I've done that actually. Some other people also have done that. So it's not helping.
I have a question. So you mentioned that in conformal anomaly you also have gauge field terms. Is there any effect of this sigma coupling to, say, Young-Mills kinetic term?
It's very similar to if you just that term. I'm just scrolling to find out. You see, that term will enter in this expression. That term will enter as this one, sigma times Young-Mills kinetic term squared. Because Young-Mills kinetic term squared in 4D is while invariant, it will just add to this one, and you can rewrite in terms of G bar or G. It's while invariant, so it's not affecting this conversation about higher derivative terms and such. It's easy to introduce.
Okay. Yeah. Thank you.
Okay. Any other questions?
What is the interpretation of this scalar mode? Is it actually one of the modes, effectively one of the modes of the quantum matter?
Okay, good question. My thinking about is the following: that GR already has that mode. It's called a scale factor. It's just that in GR, it's not a proper propagating mode. But it does some things, it gives you FRW cosmology, right? So because when you introduce quantized fields, those quantized fields make that mode to be kind of interacting non-linearly in a ways that anomaly prescribes, and then you get that problem, strongly coupled interaction problem. So to resolve that, you need to convert that mode into a proper propagating degree of freedom. And what's being proposed here is that this mixes it with the sigma. So one of them becomes properly propagating degrees of freedom, and that sigma then is the one that appears in the anomaly action. So it's all weakly coupled all the way to this M-bar scale. So that's my interpretation of it.
So it's not fundamental. It is effective.
I don't know what you mean by fundamental. It's
well, the results of integrating out some fundamental fields.
No. I mean, it's there. So it's a propagating physical degree of freedom. So it's you can measure. There is in principle, right? So the black holes have this Fifth force, which that Tsujigawa found, for instance, is precisely because of that mode. So in principle, it's something measurable.
You may say it's part of gravity. It just happens that in Einstein theory, for particular action, it's not dynamical. That's all.
You are exactly right, Arkady. Yes.
But that's not a part of this G bar field, as I understand. It's extra variable.
Yeah, it's extra in addition to the. So see, if I can rewrite G bar in this form. Now I have a theory which depends only on G and the sigma. So it's in addition to the propagating gravitational degrees of freedom. Right? In GR, let's distinguish between propagating degrees of freedom and the fields. There are only 2 propagating degrees of freedom in GR. Those are tensor modes. But there are, whatever, 10 fields. Some of them are gauge redundancies, some of them are constrained. Now here, introduction of the sigma does the following job, that it mixes with the what we call the conformal mode in GR and creates one mode which is a dynamical one, and the other one is still constrained. And it's physical then. This dynamical one is physical, and that's the one that resolves the issue of the strong coupled behavior. So if you don't want to go into these details, you can just think of this as a scalar tensor gravity. This is a scalar tensor gravity. In fact,
what is the starting point of this physical picture? So it would seem that you started from the statement that you have one of the equations of motion is just curvature scalar equals trace anomaly, which is generated by some quantum fields.
Yes.
And then you try to find such effective action with extra degree of freedom that would mimic this equation of motion. So I think that the logic of this is something like that quantum matter that induces the conformal anomaly of a given structure effectively can be represented as this extra degree of freedom. So in this sense, this is effective degree of freedom. It's not fundamental one. It would seem that the way how this can be interpreted. Maybe you have another.
Well, you can interpret that way by stating that taking Occam's razor approach, in which you say GR has no propagating conformal mode. Period. Let me not discuss cosmology or anything like that. GR only has 2 tensor modes. Period. Then this theory has now 3 modes, 2 tensor modes and 1 scalar. And that scalar came because you've kind of integrated out effectively some loops and captured in the effective anomaly action. Sure, you can say it that way. But more, I think more, better way which goes to the heart of the problem is the one in which you do think about the conformal mode of GR, which is not a propagating degree of freedom, which then mixes with this sigma field. So it's there, non-propagating, and the quantum anomaly properties makes it kind of dynamical in a sense of creating some nonlinear interactions for it. And then you need to resolve that problem, and you need to give proper kinetic time to that. That's how I prefer to think about it, tell the truth. Your thinking is more along the lines of the Schwinger model that I described. So in the Schwinger model, as we talked, in the classical approximation, gauge field had no degree of freedom whatsoever. You had just massless fermions. Then we integrated out a loop of the massless fermions, and that gave rise to effective degree of freedom, like a plasmon or exciton, something like that, which got swallowed by the gauge field, which had no degree of freedom, and now it has 1 degree of freedom because it's a massive gauge field in Schwinger model. So your logic more in that direction. I think the one that I'm proposing is a better, more nuanced interpretation consistent with what we see in GR.
So, any further questions? Okay, then thank you again for a nice talk.
Thanks all.
And thank you everyone for coming. Hope to see you next time.